input, we will have y equals to 0. Let's test for this x1, x2. x1 is 1 and x2 is 0. Okay, 0.5 is your w0. w1 into x1, 1 plus w2 into x2, it is 1, and summation of wi xi is 1.5. So if it is greater than 0, we assign it a 1. Because this equation is fairly simple, we can simply choose the appropriate value of w1s and w2s to design or OR operation specifically. So what is the key point here? What do you understand from all these two functions that we defined? What do we understand from all this? We can use the same input x1, x2 to define AND operation as well as OR operation. What is the difference? The difference is the weight values. What weight values can we choose so that our perceptron can act and operate like an AND operation or OR operation? So for 0, 0, it is y is 0. For 0, 1, it is 1. For 1, 0, it is 1. And then 1, 1, it is 1. So the same input is given, but the weights of the inputs are altered to make them behave as a either AND or an OR operation. So we can define and design our perceptron to behave in these form. Another operation that we can use, we can define as an example, is simply NOT operation. Again, we define when w1 is given and w0 is given, simply 0 or 1. So if you give, for NOT operation, simply we have, if you give 0, we should have 1, and if you give 1, we should have 0. So for that, we don't need x1 and x2. We just need one input, x. So x1 is either 0 or it is 1. And then we define an appropriate values of w0 to give the summations that lead to when input is 0, the output is 1. Input is 1, the output is 0. So now we have learned that we can define the AND or NOT basic operations for a perceptron by simply altering or changing the weights, the W's. The key is the weight values. By changing weight values, we can define or design or AND or NOT operations. So what does a multi-layer perceptron graphically looks like? Let's cascade many perceptrons, or we can call a network of perceptrons, a network of neurons in the human brain. It is analogous. So we present it as a layered structure for simplicity of learning, and for a multi-layer perceptron, that is a base for machine learning neural networks, we have 3 layers. One input layer, one or more hidden layer, and one output layer. We have 3 components: input, output, and a hidden layer. So we already studied, if we just look at one neuron, the input is x1, it is multiplied by a weight and given to this neuron. And we call this neuron a hidden layer neuron. And then if we look at this neuron at the output layer, it also has a weight. And then we know that this neuron would have a summation and a classifier, summation and a classifier to finally give our y. But it is not that simple. It is a fully connected network. A deep neural network is fully connected neural network. MLP is fully connected. Means, what does a fully connected network means? This means that all the neurons will have a connection with all the neurons in the subsequent layer. So this neuron will have a connection with all the neurons. This neuron, here, here. Again, let's look at another example. Check this neuron. It will have a connection from here, from the previous layer. Lastly, this neuron, it also has input from all the previous neurons. So all the nodes in the network, they are connected. And for the first hidden layer, it will have input from all the predictor variables, the x input and or first W0, which we call 1 here, okay, or the bias. So we should have, when we define a multi-layer perceptron, we define the input, we define the output, and we define or configure the hidden layer. Input layer, output layer, and or hidden layer. What do we mean by configuring the layer? Configuring the layer means what is the size of the input? How many variables are there? In this example, we have m plus 1. These are m variables plus for W0. We have 1, m plus 1. And for example, we have n here. So we will have n neurons in the second layer. And the last layer we have n, vector n, 1 to n neurons. So if we have a binary classification, what will be the value of n? It will be 1. Why? Because either 0 or 1. So we will only have a y which will have only 1 neuron if it is binary classification. If we have, for example, digits are from 0 to 9, so we will have 10 neurons here. If we have, for example, alphabets, for example, A, B, C, D, so we have 26. We will have output as 26 for alphabets. So the output determines what will be what are you trying to classify or identify or predict. That will be your, sorry. Okay. So the output is dependent on what we are trying to classify or predict, the number of nodes, and input is what we are trying to give as input. And each link that we have, it will have a weight. Initially these weights are randomly assigned. And then they are updated using back propagation. Or we are familiar with gradient descent. An example is gradient descent. How do we update the weights? Using stochastic gradient descent. We have already visited this topic. So first random initialization for these weights and then update the weights. So this is how we say, how we represent our neural networks. Multi-layer perceptron. Now for a simpler version, for example, in the first hidden layer, we have only 2 nodes. And the final layer has only 1 node. Okay. Also remember that the nodes start from the hidden layer, but we have to define the input size. So input layer does not have a node, but we have to define the size of the input layer. So the size of input layer here is 2 plus 1. Okay, now let's visit the concept. For the first link, we have weight. This is neuron 1, this is neuron 2. Okay, so weight from W from 1, we define it like this. From 1 to 1, we have W11. And then we have from 1 to 2, we say W12. Remember this presentation? This is your node 1, this is your node 2. So connection will be from 1 to 2.